So today I will present an image processing method which is called mathematical morphology, and I would like to talk about the potential of combining this mathematical morphology method with machine learning techniques. And yeah, actually I would like to hear your advice or opinion on this. So, oops. So first, I will quickly present this mathematical morphology method and its application to solar features detection. In particular, we use it for sunspots identification. And then I will introduce morphological neural networks, which are a specific architecture of neural networks which incorporate mathematical morphology operation inside the hidden layers. So mathematical morphology, it's a theory which is dedicated to image analysis, which was created in the 1960s by Georges Mathéron and Jean Serra. So it is used to describe geometrical shapes in images with non-linear operations. And it is based on the use of a structuring element. So a structuring element, it's an object with a known shape and a known size. And we use this object to probe the image. So we want to compare this structuring element with the objects that we want to identify in the image. So it's somehow this is quite similar to what a kernel does in a convolutional layer. And yeah, for example, if we want to identify sunspots, then we will choose a structuring element with a size like the same size of big sunspots and with the shape of a disk. So we won't distort the solar disk when we probe the image. So mathematical morphology, it is built on two basic operations, the dilation and the erosion. So the dilation, it computes the output pixel as the maximum of all the values in the neighborhood. So the neighborhood is defined by the structuring element. And the erosion, it will output the output pixel as the minimum values of all the pixels in the neighborhood. So in practice, the output image that we'll have after a dilation operation, it will be an expanded image, like we can see here. So we will have the brightest regions will be enhanced. And on the other hand, if we apply an erosion operation, then we will have a more compressed image, and the darker regions will be enhanced. So these are the basic operations, but then from that operations, we can have more useful operations like an opening, for example, which is an erosion followed by dilation. And this is useful to eliminate white noise and to separate components, for example. We can also apply a closing operation, which is dilation followed by an erosion to eliminate dark noise. We also can apply morphological gradient to find contours of objects images. And we have much more complex operations that then we can combine. And this allows us to have various applications like noise removal, edge detection, segmentation. And this is particularly well suited to the field of heliophysics because we may have solar features with sharp edges and with complex and irregular shapes, like active regions or filaments. And this is also applicable to both high-resolution satellite images and also to low-resolution images, for example, taken from ground-based observatories. Like, for example, here on the bottom left, we have spectrograms from the Observatory of Coimbra in Portugal. And on the right, we have SDO images. And we have applied the same mathematical morphology operations to identify the vacuolar regions here. And basically, we can use this method to identify almost any solar features. It could be filaments, coronal holes, or even coronal jets. But first, we have applied it to for simpler solar features like sunspots. So we have applied mathematical morphology to identify sunspots over an entire solar cycle. And visually, we can see that it looks fine, but we need to find a way to measure, to validate the method quantitatively. So for that, we have measured the sunspot areas, and we have compared with two well-established solar catalogs, the Debrecen Heliophysical Observatory database, which is very reliable because the areas have been found manually. And also we have used Mandel et al.'s catalog, which is also very reliable because it cross-validates different areas from different observatories. So on the plots, we can see the correlation between the areas that we have found with mathematical morphology method and the DHO observatory here, and with Mendel-Settles catalog at the top. So we can see a quite good correlation. But then we also need to take into account the foreshortening effect, because like when we project the sun onto a plane, then for example, the sunspots that are near the solar limb, they will appear smaller than they actually are. So we have corrected the sunspot areas for this foreshortening effect, and the areas are, the correlation coefficient are in the table here. So we can see that we still have a good correlation, not as good as the one we had with projected areas, but still it's satisfactory. So this validates the method, and now we can use mathematical morphology for more complex features. So for example, delta sunspots. To identify delta sunspots, we use intensity images from SDO to segment, to contours the umbra and the penumbra with mathematical morphology. And we are also using HMI magnetograms in order to have also information about the magnetic polarities. Because a delta sunspot is a sunspot with umbra of different polarities that share the same penumbra. So we need to combine these both images. And then the idea is to find the polarity inversion line and to calculate properties of this polarity inversion line inside the delta sunspots, like for example its length. And we would like to do that at several heights in the solar atmosphere, in the chromosphere especially. And then try to find the correlation with X-class flares. But what I would like to emphasize today is the challenges that we still meet with mathematical morphology, because the big inconvenience is the lack of automation, because it can be very difficult and very long to find the optimal mathematical morphology operations, the optimal size and shape for the structuring element. Also, we don't know how, it's a lot of trial and error, and we don't have a way to find automatically what type of mathematical morphology operation to use, or especially in which sequence we need to combine all these mathematical morphology operations. So what can come to mind is to use a neural network to try to solve this problem. So here on this slide, I have put side by side what a convolution operation does in a convolution layer, and what a morphological dilation operation does in a morphological neural network on the right, on the left. So what we can see, it's almost the same structure, but instead of multiplying the neighborhood pixels and then taking the sum, as we do in a convolutional neural network, here in the dilation layer, what we do is that we take the sum of the neighborhood pixels and then we take the maximum. So that means that we don't need to have a nonlinear activation function after the morphological dilation layer, because it's already a nonlinear operation, the maximum. So one of the first implementation of morphological neural network applied to image restoration, it was done by Mandal et al. And they used this morphological neural network model to remove the rain and the haze from images. And they have obtained very good qualitative results on their test images. So it could be worth trying with spectralograms, for example, from images taken by ground-based observatories, because like we saw yesterday, sometimes they are subjected to very bad weather conditions with a lot of clouds. So this could be interesting to try the network. So the neural network is implemented with dilation and erosion layers, and they randomly initialize the structuring elements. Then they define a loss function, so they use the structural dissimilarity as a loss function, and then they learn the structuring elements by a backpropagation algorithm. And as metrics, they have used the peak signal to noise ratio and the structural similarity index measure. So here we can see the architecture of a neural network. So we can see two paths. On the top, we have an opening path because we have erosion layers followed by dilation layers. And at the bottom, we have a closing path. So because it's dilation layers followed by erosion layers. And here we have the results that they have obtained. So we can see that both convolution neural network and their morphological neural network have approximately the same accuracy. at least for the SSIM. For the peak signal-to-noise ratio, the morphological neural network performs a bit less well. But on the other hand, it uses also significantly less parameters. Because as we can see, the traditional convolutional neural network, it has to train more than 6 million parameters, while the morphological neural network only needs to learn 16,000. So to conclude, I would say that morphological neural network is a quite recent implementation, because like the method is quite old now, but its implementation with neural networks is very recent. But it's fast to compute in terms of, because there are much less parameters to learn. And also, it could provide some interpretability. We could have some more insights into the neural networks, because the weights that are learned during the backpropagation algorithms, they correspond to the structuring elements of the morphological neural network. So this can give us some geometrical and topological information, because intuitively we can understand a bit better how the image was processed in terms of geometrical operations. So some potential leads for improving these morphological neural networks, for example, it could be to use more complex mathematical morphology transforms, because for now it has been very basic ones. And also it could be interesting to use more like hybrid neural networks, not only convolutional layers or not only morphological layers, but a combination of both. Also hybrid networks with, for example, genetic algorithms, if we have a very complex morphological pipeline, or we could also use recurrent networks, especially if we have iterative morphological operations. And yeah, and besides morphological neural networks, also another interesting application of morphological neural networks, it's what we can call the chip labeling. So that means that we can just label a dataset with morphology, because it's quite fast, and then we can train machine learning algorithms on these labeled datasets. So yeah, thank you.
Thank you. Do we have questions? Yes, please.
Thank you, Slava. Interesting. A question I have is, you mentioned that you can apply this method to different solar features, right? From sunspots to filaments to whatever. What do you use as input for a given feature? For example, in sunspots, do you use just images of sunspots, or what do you use? Do you use different wavelengths? How do you provide input to this model?
So for example, for sunspots, it's only intensity images. For filaments and active regions, it's chromospheric images. And, but for example, for delta sunspot identification, then I need to combine both magnetograms with intensitygrams.
Okay. So you might have either single images or combinations of images,
yes, exactly,
as input.
Yes.
Thank you.
And I was wondering, thank you so much for the presentation, it was really nice. I was wondering if the mathematical morphology approach is like some unsupervised learning process, or you use anyways like an input data and then you reproduce like a mathematical process to generate an output? And
yeah, because it's not machine learning, so it's just operating some mathematical operations on the data.
okay, so do you have think about how to just, like, for example, you mentioned that you can be easily labeling structures without any input, like you.
Like the input is the image, yeah. And
yeah. So this is like could be, if you think that like an applicable for unsupervised learning process, classifying things that we don't know what it is.
I mean, we can use like to label data, and then we can train, for example, an unsupervised algorithms on this. Maybe I don't know.
Okay. Well, let's try to discuss this. Like,
yeah.
Probably.
Hi. So this is really, really interesting. This is something I've been wondering about how to do for a long time, and it's a completely different way than I would have expected. So I'm just wondering, a very simple but important transformation that I'm not sure counts as morphology is a translation, and can this manage with translations as well, or would you then have problems identifying when an object or shape is the same as in previous moments? I can rephrase if that question didn't make sense.
Yes.
Okay. So if your object, instead of like shrinking or growing, moves, can this method deal with that, or would that require more
that's
thinking?
the problem with it, and that's, I think this is where machine learning could be very interesting, because we need to it's manual. We need to try so if a shape is moving, then we need to manually change the size, the shape of a transform. But maybe with machine learning, then we can deal with this and make it automatic, in some way, if we can combine both.
Okay, that's really interesting, because most of the applications that I would find from this are for one shape shrinking or stretching and moving around. So thank you for this. I've got lots of thinking to do.
As on solar images, you may have several features appearing. How would you discriminate, for example, sunspots and the dark areas that are in between faculae at the edge of the limb, for example?
Like the small dots that we can find in faculae sometimes, or
Yeah,
but like for example on intensity images we will only see the sunspots.
Okay.
But otherwise, like what we could do is just to try to change the shape of striking element. So, like if for example we will take only circular shapes or only line shapes for only taking the filaments and not the sunspots, for example, we can also try to apply some directional morphological filters. So this depends on the direction. So maybe it could also help to discriminate between features.
okay. Thank you.
Any other questions here? Okay, we have one question online. Maybe could you please unmute yourself?
Yeah. Hello. So can you hear me?
Yes.
All right.
Yes.
Yeah. Okay. I think the previous question was about umbrae and penumbrae. So how do you distinguish between umbrae and penumbrae in sunspots?
So this is just based on the intensity levels.
Okay, so you are able to do that. And you are not applying any thresholding after, I mean, the mathematical operation does some dilation, opening, as you said, but if you want to extract the sunspot, then you need to put some threshold, right?
Yes, exactly, yeah.
Okay. And so there was a poster yesterday that was mentioning that, you know, you could use different level of threshold and then actually pass that onto a convolutional neural network that will then decide which is the best. And basically you do not choose one threshold, but you let you put everything as a feed to the neural network, and then it alternates. It once pick one mask obtained with one threshold, then at the next iteration it picks up another mask obtained with another threshold. It alternates, and basically you find the best. So what I'm saying is that you could also use the CNN, provide as much information as you need to the CNN, and then make him decide what is the best option during model training, actually.
Yeah, this is a very good idea, yeah.
But this is very interesting also, and yeah, thank you very much, and I liked a lot your